Okay, so we're now going to take a look at the mass spectrometry and its use in organic chemistry. You've come across mass spectrometry early on in the year. You would have done mass spectrometry generally to identify the different isotopes of an element and the relative abundance of each of them, so you could calculate the relative atomic mass from the proportions of the different isotopes. We're not generally going to come across isotopes very commonly in organic chemistry, though it does come up for a couple of key elements. We're mostly using it as a tool towards structural determination, primarily finding the MR of the chemical. So we can work out the empirical formula from those percentage by masses. To find the MR, we're going to use mass spectrometry. So when you've done mass spectrometry before, let's say we maybe took xenon, you will have ionized that. The one you learnt about is something called electrospray ionization, or sometimes called ESI. So that's where you dissolve the chemical up, put it through a very thin needle that's attached to a high voltage power supply, I believe is the language they use in the A-level course, and that takes an electron off the molecule, or off the atom in this case. So you will have formed xenon plus ions. Now, this is a little bit of it's very much a bit of a simplification, because ESI, electrospray ionization, doesn't work for these kind of things. But what they don't want to overcomplicate things by having multiple different ionization techniques. So ESI, it doesn't actually form Xe+, though you would form Xe+ if you were doing mass spectrometry of individual elements like xenon. ESI, actually what happens is the solvent that your molecule is dissolved in. So if we'll take some methanol, and we'll say that's dissolved in a load of water. So we've got a load of it dissolved in water. What happens is the hypodermic needle that you pass this mixture through, the solvent, or it could be this directly, but generally gives up an electron to the positively charged needle, and it generates a bunch of H+ ions. So we've got a bunch of H+ ions, and that H+ ion is generally going to attach itself to all the molecules in there. So this is our chemical we're testing for by mass spectrometry. So that CH3OH is going to react with the H+, it's going to attach itself onto it, and we're going to form CH3OH2 positive. So it protonates the molecules. So it gains a positive charge, not by directly ripping an electron off of the molecule, but by adding an H+ onto it. Now that doesn't take place with something like the xenon, but with the organic molecules that we come across, generally with things like an oxygen that has a lone pair that can act as a base, it can attach it, so it can share electrons with that H+. We form these things here. Now the kind of notation we often use in mass spectrometry is we're going to call this molecule here, the thing we're testing for, we're going to label that as M, which sort of stands for our molecule. And so that's going to react with H+ to form MH+. And so what we're actually going to see in electrospray ionization mass spectrometry is we're not going to see a peak for the molecular ion M+. We're not going to see that because we're not going to directly remove an electron from the molecule. What we're going to see is M plus H, all positive. So we're going to have M, the molecule, attached to a hydrogen with an overall positive charge. So you should be familiar with what the spectra look like, where we have the MR, mass over charge ratio, and the abundance. Now the spectra you're going to be presented with, again, it doesn't actually match what these spectra look like, but they simplify it to make it simple, because it does get quite complicated. You're going to see a whole bunch of peaks, and the rule you need to use is whatever this last one is, that's your molecular ion. So if we were testing xenon, you would have gone, oh, that's just a molecular ion, that's M. Well, that's not the case when we're using electrospray ionization of organic molecules. That's going to be M plus H with a positive charge. So let's say this comes out, let's say this came out as 73, so the M over Z value was 73, that means our M actually has an MR of 72, so it would actually be 72. So you just need to subtract 1 from it, whereas if you are doing it for your inorganic chemistry, you just take the values as face values. So if you've got the different isotopes and it comes out as like 101, 102, 103, you just take those and do your relative atomic mass calculation. When you're looking at this, we're not looking for the different isotopes. We're just looking for what the mass of the molecule is, and the final peak you're going to see is going to actually be the molecule plus a hydrogen. So you need to subtract 1 from that mass. So you find it 73. Well, actually the mass is 72. Now you need to be careful when reading any textbooks for A-level about this, as AQA initially made a mistake with all of this. So I understand that they were trying to simplify things, and I'll be honest, they made a bit of a mess up with simplifying this, and they published a document a year after the course was first started in 2015 or 14, and they released a document basically clarifying things, and so making it clear that the M plus H is what's formed, not M plus. Whereas they initially said that this is what happens to organic molecules, which is simply not the case with electrospray ionization. So if you go on to the supporting information on the AQA page for your course, you'll see it on there about like an information sheet for students about mass spectrometry. You could have a read through that as well. I'll see if I can download that and upload that onto the Bow space for you. So the only time you might come across isotopes showing their head, sort of rearing their head inside organic mass spectrometry is really with the halogenoalkanes, specifically with bromine and then with chlorine, if that's in there. So the bromine one is probably the simplest because it's got a roughly 50-50 sort of distribution of these two isotopes of bromine 79 and bromine 81. With chlorine, it is 25% chlorine 37 and roughly 75% chlorine 35. Now, if you were to take the mass spectrum of chloroethane, so bromoethane, we'll have all the peaks down the bottom, but we're going to have 2 molecular ion peaks, or in this case M plus H peaks. So there's going to be the mass of the molecules is different depending on which isotope of bromine it has, and it's pretty much a 50-50 chance for each molecule which one it's going to be. So we're going to have a peak at 111, so where the one which has a bromine 81 has an MR of 110. So if we add an H plus onto it, we're going to have one peak at 111 for the M over Z ratio. And then if it has a 79 isotope, we're going to see a peak at 109. So you need to, if we're dealing with bromine or with chlorine, you're going to see a pair of peaks at the top. For bromine, they should be roughly the same intensity as each other, or same abundance as each other, at 109 and 111 for this. If it's a different molecule that contains a bromine, it could be at any other M over Z value. For chlorine, because you've got 75% of 35, so the 35 chlorine is 75% of it, and the 37 chlorine is about 25%. You're going to see 2 peaks next to each other, same with the distance of 2 between them, but they're not going to be the same height. It's the one slightly lower down, the 2 down, is going to be 3 times the height of the one which has got a 2 heavier than the other one. But remember, these are both M plus an H, M bonded to an H positive. They're not M positive, so you still need to subtract the 1 from it.